Step 2, 2005, question number 5. It's also question 8 of the Miscellaneous Pure Step 2 Sport module. We're looking at a triangle that's right-angled and it's all labelled like so. And we have a circle in which every side is tangent. Every side of the triangle is tangent to the circle. So the circle must be inside like this here, radius r, which also means r is here and r is there, I guess, as well, by, it's just a circle. Show that 2r is this thing here. So, okay, well, if r is there, then r is also down here as well, which makes this length across here b minus r. And then if you take this quadrilateral over here and maybe split it in half, you can see that these are two right-angled triangles, because there's a right angle here between radius and here, and tangent. Which means by RHS, right angle, side, and shared side, these two triangles must be congruent, so this length here is also b minus r. And up here as well, same thing, exact same deal. So that's length there is r, so this here is c minus r, which means that's c minus r, and then we could just look at this and go a equals this plus this. And if you rearrange that, you'll end up with the thing they want you to get. Good. So now we have this here. Each vertex of the triangle lies on S2. So this S2 triangle is much bigger, going around the corners of the triangle a bit like this. And now because this is a right angle, key thing here, because that's a right angle, this is the diameter of the circle, BC, which also means half A is the radius. And then it says the ratio of the area of the region between S1 and the triangle and the big triangle is r. So okay, the area of the big circle. The area of the big circle is just pi times this squared. The area of the little circle is obviously just pi r squared, and the area of the triangle is a half CB. So therefore, the area of the region between S1, which is the little circle, and the triangle is this, take away that. And now the ratio r is between what I just said there and S2, means I'm going to say r is this over S2. And that'll be all of that good to go. So now I think I just need to try and make this happen, where Q is this. So, okay, which of these letters does this not have? Well, it doesn't have any of them, except Q is made of B, C, and A. So actually, I just need to get rid of the R here, and then try and fashion the B, C, and A into kind of things that look like this. So, okay, well, R we already have a thing for. R is this. So I decided to double top and bottom of the fraction, and then I did it again, because that way 4r squared can become 2r all squared, and I can just put this 2r straight in. And then I did some expanding out. When you expand something like this, you just times this one by itself, this one by itself, this one by itself, and then have two lots of all the cross terms, and you get all of this. And now, if you expand that out a little bit more, what we need to do is we need to constantly, I've also times everything by pi at some point as well to get r pi, because that's what they're looking for. Because what I'm doing is I'm just going to look at this as hard as possible and try and reverse engineer it. Now, what I could do is I could just start here and start expanding that out and sort of meet my way halfway. But just to be fancy, I'm going to do it all the right way around, just because it's a bit more difficult that way. But, whatever. It's more fun. So looking at this as carefully as I can I try and fashion this stuff into this stuff here? Well, okay, there's a minus pi here. I look at this term here. If I just get rid of that away from the fraction and say it's all of this without this bit minus a squared pi over a squared, that will just be a minus pi, right? Because a squared over a squared is just 1. So I can get rid of that. I can also, what I decided to do was separate these terms as well away from this fraction, because then I can cancel one of the a's and get left with this. And also this term here this term here was a bit of a weird one. So I put that on its own as well. So now I've got these three things. Now the reason I separate them out of this is because this looks pretty good to me. I think this can be factorized after a bit of work into something like b plus c all squared. And looking at the object q that I'm trying to get, that seems very helpful. And likewise here, this is why I split out these two terms as well, was because I could factorize this to be 2 pi into b plus c all over a. But b plus c over a is just q. So this is going to give me the 2 pi q that I need there. So that's why I did that. And now this I'm not sure what to do with, but I'm just going to leave it as it is. So I'm going to do all the things that I said I would. If you factorize out a minus pi from there, you're going to get a minus pi into b plus c all squared over a squared. Now, that's going to be q squared, right, from there. So this is minus pi q squared, which is nearly what they wanted me to get. This is perfect, and this is almost perfect. I'm just missing another minus 1. And now this is still a bit weird. So we need to figure out how to fix those issues, how to get another 1 in here, and how to get another 1 in there, and how to get rid of this. Now, often the case of putting 1s in the correct thing is often a case of kind of adding things only to take them away again, just putting stuff in. Kind of adding 0 or timesing by 1, doing fake things is often the case, and that's exactly what I'm going to do here. So this is all that I said that I had done already. But now looking at this term here, I think I'm going to write that as b squared plus 2bc plus c squared, only to then take away b squared plus c squared later. Because now this is going to factorize to, and I've kind of unfactorized this. I'm not sure why I did that, but I've kind of unfactorized it again. Maybe just to so you can see that these two things are now, when you look across these two fractions here, you can factorize out this whole object here to leave behind all of this into minus pi plus 1. Or if you put the minus all the way out there, minus pi minus 1 into this, which can then refactorize to b plus c all squared. So that's all looking perfect now. Now, what about this term here that I had to introduce in order to do this adding 0 in a fancy way? Well, now we have to remember going all the way back to the shape we were looking at. There it is. We haven't used it before, but a squared is equal to b squared plus c squared in this triangle. So this is just a squared, which makes this whole thing 1. And that's where the extra 1 comes from as well, that was in the formula as well. And then it all tidies up and where you all have the thing that they wanted us to get, which is fantastic. Now, deduce that r is less than or equal to this. So what I chose to do here, and I don't know whether this is the best way of doing it or not, but I chose to rearrange what we've just done into this and just call this a, this b, and this c. And I decided to just use the quadratic formula for q. So q is equal to this thing here. And now things go quite well here. You can factorize out a 4 from this third, and then take it all the way out to become a root 4, which becomes a 2. And then a lot of 2's will cancel. And also when you expand all of this out very carefully, a lot of it cancels. Like these two cancel, those two cancel. You're left with a bit of stuff here, but it's not too bad. And now looking at this here, I think I chose to factorize out a pi from that bit there. Yeah, I just factorized out a pi from the inside there. I'm not really sure why I bothered to do that. But anyway, looking at this, I think I need to meet the condition such that this thing here is greater or equal to 0, because I'm square rooting it. So this thing here must be greater or equal to 0. So therefore, I can say that, and then I can move the thing over and then divide by all the remainder, and we'll end up with this here, which is what they wanted me to get. And I think I am done. Thanks for watching.